This video is going to derive the gain bandwidth relationship for the non-inverting and inverting op-amp configurations. Here's a full picture spoiler for the final result, is that there's no gain bandwidth product for the inverting op-amp configuration. But I'll start with the non-inverting and then go into the inverting. Here we're assuming the op-amp single pole response with a DC gain of A naught and a open loop bandwidth of little omega naught, and we're going to define a closed loop bandwidth capital G naught and a closed loop gain capital G naught, closed loop bandwidth big omega naught. And here's our setup for the non-inverting. Two equations: V out equals A of S, which is the transfer function we're used to with the open loop transfer function, times E, which is the difference between the non-inverting and inverting terminals. Substitute just nodal equations into one another, and we get this. And if we multiply by 1 to kind of rearrange the terms, we end up with this. Now, if we sub back in what A of S actually is, which is A naught over 1 plus S over omega naught, we're left with this guy here. And if we distribute the terms into the 1 and the S over omega naught, we can say that this term goes to 0 because A naught is 100,000 or a million. This is on the order of 10 or 100 max. And we're left with this guy here, which is also in the form of a typical single pole transfer function, where the gain is 1 plus R2 over R1, and the new 3dB point is omega naught A naught over this gain here. And if we define this as our new closed loop bandwidth, we see that we have this relationship where the configurable gain in the closed loop bandwidth is equal to the open loop bandwidth and the open loop gain. And that is the gain bandwidth product you're used to hearing. But this relationship does not hold for the inverting op-amp configuration. So if we do the same analysis here with our two equations, V out equals A sub S times E, you can use superposition or just node voltage to find what this inverting terminal voltage is. But we're left with this equation here. And again, if we just solve for the transfer function, multiply to make the denominator look nice, we get this. And if you sub in what A sub S is, again, we can generalize that this term goes to 0. If this is about 100 max, this is about 100,000. And we're left with a new single pole transfer function where the DC, or where the closed loop gain is R2 over R1, and our new 3dB point is A naught omega naught over 1 plus R2 over R1. So which is the same 3dB point as before, but the gain is different. So we cannot say the gain bandwidth product holds true here. We could say that if R2 over R1 is much greater than 1, then we have something similar to the gain in the numerator here, and we can say it holds true. But in general, it does not.